Okay. So we are discussing about different types of heating. Okay. So then different process of heating: conduction, convection, and radiation. So now, what are the important parameters? Okay. So what are the important parameters for a good heating elements? Okay. That we need to know. Okay, so we know that we are using water. Okay, water having high specific heat, MST. Okay, so for high specific heat, that's why what happened, it having some capability to store the heat for more duration of time. Okay, so heating of water also taking some more time, and as well as it having high specific heat, so that's why it having a capability to store the heat energy for more time. Okay, so what are the more essential requirement for good heating element? So first we are deciding about that high specific resistance. Okay, then high melting point, low temperature coefficient of the heating, free from the oxidations, high mechanical strength, non-corrosive, and finally economical. So first one, that material used for the heating elements for following properties. Okay, so high specific resistance. Okay, so material you are using that having high specific resistance, so the small length of wire may be required to provide the given amount of heat. So high specific resistance means, so for small durations of that objects, okay, you will get more density of that heat. Okay, so high specific resistance. Okay, high melting point, so those material having more melting point, so more heat required. Okay, more heat is required to melting the element, so that may be the that temperature is more than your oven temperature, so that can also serve your purpose. Okay, so it should have high melting point. Okay, it should have high melting point so that it can withstand for high temperature. A small increase of temperature will not destroy the elements. Okay, or you are using that electrical oven. Okay, so which bowel? Okay, where that you are going to use the charge. Okay, you are using charge material. Okay, for the melting purpose. Okay, that container having high melting point, low temperature coefficient of resistance. Okay, that the radiant heat is proportional to the fourth power of the temperature. Okay, radiant heat. Fourth power of the temperature is very efficient. Heating is high temperature. For accurate temperature control, the variation of the resistance with the operating temperature should be very low. Okay, this can be obtained only if the material has low temperature coefficient resistance. These are the very specific requirements. Okay, then free from the oxidation. So what material you need to use, that should not be oxidized. Basically, at that points it should not be chemically active. Okay, you know that increasing of temperature, increasing of the pressure. Okay, when we are studying in chemistry. Okay, there are some environmental conditions for that chemical combinations. Okay, at the time of, suppose we are using that production of that ammonia. Okay, so 3/3 volume of this one with combining with another return at that 300 degree centigrade. Okay, with that atmospheric pressure. Okay, different conditions are there. Okay, so that whatever element you want to use here, that should be free from oxidations. Means what temperature you are going to use, that should not be accelerate the chemical process. Okay, that should not accelerate your chemical process Okay, means it should be like that. That's temperature value should be below of that. Okay, otherwise it will be oxidized. High mechanical strength. Okay, so the material should have high mechanical strength and should withstand for the high mechanical vibrations. Okay, so vibrations also important. So high vibrations mean that you may lose that material. Okay, non-corrosive. Okay, the elements should not be corrode with the exposed atmosphere or that other chemical forms. Okay, so suppose sometime materials are there, you know that automatically oxidize with the presence of elements in your air. Okay, so that type of thing should not be used. Okay, non-corrosive material you have to use. End of the day, the cost of the material should not be very high. Okay, so these all are the very simple and required parameters. Okay, essential required parameters for good electrical heating. Now the most important portions is there. What are the basic classifications of electric heatings? Okay, electrical heating methods are the more important classifications. First one is that electrical heating is there. Okay, so two types of segregate two types: power frequency heating, another is a high frequency heating. Okay, so for power frequency heating, what happened? Resistance heating. Okay, you are using resistance heating. Okay, arc heating and electron bombardment heating. Okay, power frequency heating means normal frequency, means whatever range of your applications, power range of application, it is 50 hertz. Okay, in our culture we are using 50 hertz. High frequency means it is very high frequency. Okay, maybe normally where hearing range is 20 to 20 kilohertz. Okay, so that frequency is beyond that one. Okay, beyond our audible zone. Okay. Hmm. So that is your high frequency heating. Okay, more than 20, sometimes more than 20 kilohertz. But normally beyond 5 kilohertz, it is also called that high frequency applications. Okay. So it is, what are the different types? Induction heating. Okay, dielectric heating. So these are the applications for high frequency heating. Again, induction heating can be classified direct induction heating, indirect induction heating. So all of the heating process may be categorized direct method, indirect method, sometimes hybrid method. Okay, so all kinds of things are possible. Okay, so whatever your requirement, okay, based on that you have to whatever your requirement, based on that you have to select that process. Okay, suppose resistance heating is there. It is an example of a power frequency heating. Okay, it having three types: direct resistance heating, indirect resistance heating, another is radiant or infrared heating. Okay. So arc heating also having two methods. Direct arc heating means arc is directly involved. Okay, the arc is directly involved with that heating process. Okay, means charge is there. The direct arc is flowing through the charge. Another one is indirect arc heating. Okay, and you know that now individually will going to be discussed. Okay, for electrical heating, sorry. For electric heating can be broadly classified into two categories. Okay, two categories. Number one is that power frequency heating, in which the furnace operates with 50 hertz. Okay, 50 hertz decibel supply. Point B is that high frequency heating. This is your high frequency heating, in which the special high frequency generator is essential. Example, the dielectric heating or induction heating, both can be used for high frequency. Okay, broadly classified. That I am talking about the power frequency, that is 50 hertz. Okay. Now for power frequency heating, we will start with that first. What type of heating? That is resistance heating. Okay. Then resistance heating. In resistance heating, what I mean again, resistance heating happy resistance heating are again categorized into three methods. One is direct resistance heating, indirect resistance heating, and radiant or infrared heating. Okay. So for direct resistance heating, the electric current, okay, the electric current is made to pass through the substances. Okay, current is made to pass through the substances to be heated or charge itself. Means I am talking about the charge. So charge means that material that going to be heated. Okay, that itself itself heating. Okay, directly. The electric current, okay, the electric current while passing through the charge product I square R loss. Okay, so I square R, that R is also been in the part of the charge. Okay, that R portions also been considered as a part of that charge. Okay, that when plus that charge. Okay, so directly charge is carrying the current. Okay, so I square R T. Okay, that due to that I square at T heat joule, okay, it will be automatically melting down. Okay, but problem is that high energy, high power loss will be there. Okay, the loss which appears in the form of the heat. Okay, thus the charge is heated up. Okay, simple understanding. Few example in this heating method are resistance, resistance welding, electrode boilers. Okay, for heating water, salt bath furnace. These all are the examples. Okay. Indirect heating, what happened? The charge is not directly. The charge is not directly uh, carrying the current. Okay. Okay. Directly not involved with this high current. Okay. The current is passing through the heating element. Okay. Current is passing through the heating element. I square loss produced will appear in the form of heat. This heat is passed on the substance or charge to be heated by radiations and convections. Means directly they are not involved. Okay. Direct conduction is not involved. Okay. It can be heated through radiation. Okay. Or it can be heated through other method like convections. Okay, but they are not directly involved with that heating. Okay, and direct current is not present, but still the there is the inductions is there. So due to inductions, okay, due to induction current will be developed over there, and that current I square R is the resistance of that charge. Okay, T. Okay, I square at T, that may be responsible for heating. Okay, so room heater is example. Hair dryer, soldering iron, immersion water heater, water plate, frying pan, electronic oven. Okay, electric oven. These all are the induction heating examples. Okay, radiant heating or the infrared heating. Heat energy from an electric lamps. Okay, heat energy from an electric lamps is focused on the charge to be heated. The heat energy is transferred. The heat energy is transferred through the electromagnetic radiations. The electromagnetic radiation, it is transferred. This is used for drying the paints of the objects. Okay, drying the paints of the objects. So it is, you know, that before of that any occasions. Okay, those are working. Working or designing that different idle. Okay, so very quick drying is required. So they are using that methodology. Okay, uh, for drying up that idol. Okay, directly. Suppose painting is there, they are trying to drying up that painting. Okay, so moisture can be removed from that painting. Okay, by this method they are using. Okay, arc heating means arc directly, same similar type of options. Okay, arc heating, again direct arc heating, indirect arc heating. Arc heating means that charge is behaves like an indirect arc. Normally arc is happened observed in which terminals? Okay, normally for two terminals of the electrodes. Okay, the terminals of the electrodes. Okay, so one of the electrode will be your charge material. Another electrode will be as it is. Okay. For direct heating, direct arc heating, okay, arc heating, I mean direct arc heating, the arc is made to strike between the electrode and the charge itself. Okay, so charge itself behaves like an electrode. Okay, for direct arc heating. So there is a arc is developed, and due to the presence of that arc, okay, it will be melting down. Normal resistance, what happened? I square R. Okay, so there is a medium. Okay, direct medium is there. Okay, for developing that heat. So current is flowing through that medium. Okay, then it is entered to the charge. So loss is more in resistance setting. So arc heating, what happened? Loss is comparatively less. As that arc means it's breaking down of that atmosphere on the durations. Okay, that in between two electrodes, and that electrodes medium is flowing the current, and that current directly passing through that electrode, passing through that charge. Okay, then it is then it try to melting down that charge material. Okay, the heat energy of arc is absorbed by the charge, and thus heating is done. Okay, indirect arc heating, what happened in indirect arc heating? An arc is made to strike between two electrodes. Okay, the heat of the arc then pass on the charge through the radiations. Means what happened? Directly arc is not passing through that material. Okay, suppose two electrodes are there. Okay, two electrodes are there. Just below of that two electrodes, one charge material container is there. That material container contains that charge elements. Charge element means that melting elements. Now arc is there. Okay, due to arc, what happened? High current will be flowing, so that current may cause for development of the heat energy. That heat is going to be indirectly melting of that materials. Okay. Electron bombardment heating, electron bombardment cause also bombardment of electron may cause also. So if you suppose like the you can so electron bombardment means you are suppose you can think like that way. Okay, so you are having electrode, you are energize the plate. Okay, you are energize the plate with having some coil. Okay, so automatically what happens? So more heating means after sometimes the electron will be start emitting from that plates. Okay, so again it will be heated. So if you use a reverse thing, so same reversing, if you done it, so definitely it may cause for also heating. Okay. These all are the very basic examples, an idea about that power frequency heating. Now we can talk about that high frequency heating. Okay, in high frequency heating, what happened? The induction heating. First one is that induction heating. Okay, in this method, the current are induced. Okay, the current are induced in the charge by electromagnetic induction action. Okay, electromagnetic induction. Okay, and circulations of this current in the charge cause its heating. So charge means your melting material. Okay, due to induction, current is circulating through the charge material. Okay, so as the current is circulating through the charge material, so inherently I square T means joule will be developed. That may cause for melting of that material. This is used in metallurgical industries for melting of the metals. Okay, so this is high frequency sorry. So this is an example for a high frequency heating. Okay, induction. Okay, so what happened in induction means directly current means current is developed due to inductions. Okay, not direct conductions. Okay, and you know that it's a high frequency. So high frequency means the benefit is that the other associated materials, okay, means elements, suppose inductor, capacitor, their sizing also very less. Okay, and the designing of the coil is quite easy to getting easy to achieve such amount of value. Okay, that's why it is cost efficient compared to your power frequency heating. Okay, for direct induction heating, okay, current are induced in the charge, inside of the charge, by electromagnetic induction action. In case of steel and other materials, these current are sufficient enough to melt the materials. The equipment, okay, the equipment used for the melting is known as the induction furnace, and the process used for the general heating heat transmit known as the eddy current heating. So induction furnace means current is developed due to the induction power, due to the inductions, and that furnace is known as induction furnace. And the circulating current and the material will be melting down by using that circulating current, that is also known as eddy current. Okay, so in indirect, that is direct induction heating. Okay, indirect induction heating, what happened, the eddy currents, okay, that eddy currents are induced in the heating elements, by electromagnetic inductions. Okay, the heat so produced is transferred to the charge by radiation and the convections, and the certain heat treatment method may use for this method. So the indirect induction heating, what happened, the charge will be heated. Okay, the charge will be heated by indirect methodology. Okay, not direct methodology. Okay, so directly it will be indirectly melted down, okay, by using radiation convections, not direct conductions. Okay, so I hope all of you able to understand what is the basic idea between that difference between the direct and indirect heating methodologies for different frequency applications. Dielectric heating, this is also an example for high frequency heating examples. Okay, for dielectric heating. Okay, normally induction heating, you can say like that. You can also use it for conductions. Okay, so means metals. Okay. Metals, but dielectrics normally used for the non-metals. Okay. Dielectric loss. Okay, dielectric loss is produced in the charge itself when it is subject to alternating electric fields. Okay, the dielectric loss appear in the form of heat, thus charge is heated up. Okay, so you are also using the charge by dielectric method, means high voltage you are appear across that medium. So dielectric means insulating material. Okay, there are two plates, in between two plates on insulating materials are there. You are heated up that materials. Okay, automatically it is charged up. Okay, especially you are using this methodology for non-metals. Next one is the resistance setting. Okay, in details. Okay, initially we have discussed about the resistance heating in brief. Okay, now we are discussing about the resistance heating in details with diagrams. Okay, and how it will be look like everything. So will be discussed here. Okay. So in resistance heating, okay, in resistance heating, what happens when current is passing? Okay, when current is passing through a resistance, the power loss take place, there is a which appears in the form of heat. Okay, so power loss is the form of heat, conversions of energy. Conservation of energy means energy cannot be destroyed, cannot be generated, only it can be converted. Okay, so same thing also happens. Power loss be here energy loss, okay, in the form of that power loss in the form of heat energy. Okay, and you are utilizing that heat energy. Okay, the electrical energy converted into the heat energy, H equals to I square RT. Power loss equals to I square R watts. So it is known as VI watt. V square by R watt. Okay, where R is the resistance of the element, that is rho. V equals to voltage, I equals to current in ampere. Okay, RVI. So all are the components. So here we can see the diagrams of the direct resistance heating. Okay, so electrodes are mandatory, both the cases. You know that two electrodes are there. It may be that electrodes may be different components. It may be copper. Okay, normally we are using carbon. Okay, AC DC power supply is given. Okay, AC or DC power supply, any of them are given. So high resistance powders are given here. Okay, so the layer is given actually, the charge material. So this is solid one, and you know that is a jacket. Okay, why the jacket is important? Jacket is important for if you are not given that insulating surface. Okay. Hello. Hello.
That to retain inside the charge.
Am I audible?
Yes, sir.
Any problem? Please tell me.
No, sir, no problem.
Yes, so here we can use that jacket. Basically, that power loss is there. Okay, that power loss is converted to the heat energy. Okay, that should not be a radiate from one surface to another surface, as well as there are different other protections also given. Okay, so any of the possibilities that heat should not be coming from internal surface to outer surface. Okay, so getting efficiency, when increasing the efficiency. Okay, that's the basic considerations. Okay, this is direct resistance heating. Okay, so if there is a potential difference means automatically that charge material after gradually increasing of there is a variable power supply. Okay, so gradually increasing of that heat means automatically the material will be charge material will be melting down. Okay, after certain time it will be totally melting down. Okay, so in this method what we have observed, okay, in this method the electrodes are immersed, okay, immersed in the material or the charge to be heated. So immersed inside of the materials. Okay, the charge may be in the form of powder, pieces or liquid. Okay, the electrodes are connected maybe in AC or DC supply as per your requirement. Okay. When metal pieces are to be heated, the powder of highly resistives is sprinkled over the surface of the charge, the pieces to avoid the direct short circuiting between the electrodes. Okay, so high resistance melting means it is not going to be melted down. So there is a no chances for electrodes. Otherwise, the charge contains maybe liquid and there is a high chances for the short circuiting. Current flowing through the charge, the heat is produced in the charge itself, so that the method is has high efficiency. Okay, so automatically I square T inherently the huge energy losses will be there, heat energy that will be melting down. As the current as the current in that case is not variable, so the automatic temperature control is not possible. Okay, so only possibilities is that you can increase or decrease the voltage of that electrodes. by using the power supply. This method of heating is employed in solvent furnace or the electrode boilers for the heating of water. Okay. Now indirect resistance heating. Okay, in case of indirect resistance heating, you can see that direct connections is not there. Okay, two electrodes are there. Okay, so here you can see that resistive heating elements are given, not electrode. Resistive heating elements are given. Okay, but they are not directly given inside. Charge is there, but they are not directly given here. Okay, so indirect resistance heating. Okay, the AC or DC power supply is there. Okay, this is your heating chamber. Okay, resistive heating elements. You know that is resistive heating elements. Okay, charge elements are connecting over there. Okay, this is indirect resistance heating. Okay, so if you give him the power supply on, so automatically due to that heat energy, your charge material will be melting down. Okay, what are the important features in this method? Okay, in this method of heating, electric current is passing through the wire or outer high resistance material forming heating element. So current is passing outside. Okay, the heat proportional to I square L loss. It is proportional to I square L loss produced in the heating element is delivered to the charge by one or more of the mode of transfer of heat. That means convections or the radiations. Only these two methods is possible to implement for indirect heating. Okay. An enclosure known as the heating chamber is required for heat transfer by radiations. Okay, heat transfer by radiation and convections for the charge. For industrial purpose, where a large amount of charge is to be heated, then the heating element is kept in a cylinder surrounding by jacket containing the charge. Okay, so outer surrounding a jacket is required for not it is helpful for not dissipating the heat energy for internal source to your external source. The arrangement provides us uniform temperature. Automatic temperature control can be provided. Okay. Both AC and DC supply can be used for the purpose of full main voltage depending upon the design of the heating element. As they are not directly charged, okay, so automatic voltage control can be possible. Directly charged means charge directly not involved. So only there is a heater. So you can also maintain the temperature of the heater. Okay. Some numerical problems are there. You please noting down or take a snapshot. Okay, these two numericals. Okay, and try to solve it in your home. Okay, take a snap on it. This is and some of the numericals. Another numericals are also given here. Okay. You need to put the formula and solve this one. Okay. So today I'll cover up to this portion. Okay. In next class again we'll start from the pending for our next slide. Next Monday again we'll start from that side. Till now, any queries from your end? Any queries from your end?